Welcome all. New semester, first meeting, Jagiellonian TCS seminar. Welcome all our guests online. Special greetings to our new faculties, Hugo Giocanti, Clément Legrand, and Christian Gajdzica. So we have a seminar weekly. This year we moved from 4 p.m. to 2 p.m. This is information for most of you that showed up before. You can find all the stuff online, including our speakers for the next month. Today we are happy to have Michał Seweryn. This is not so unusual to have Michał here, but we are especially happy because of your new result and that you are going to speak about it here. The floor is yours, Michał.
Thank you very much. Let me first start by thanking the organizers for giving me this platform, this international platform, to spread the good news for graph minors. The good news is in the title of my talk. And can we make it? Sorry, can we?
Yeah, it's okay.
Okay, sorry, we had this pop-up earlier. So the good news is in the title of my talk. The graph minor structure theorem holds with polynomial bound. This breakthrough discovery was made independently by me and by Maksymilian Gorski with Sebastian Widerek. When I found out about their proof, we got in touch and we realized that basically we have the same proof with only some small differences where our proofs complete each other. So today I would like to tell you a bit about what we proved, what are the applications of this thing, and how did we prove it. Let me start by giving you a crash course on graph minors. So we'll start with some definitions. What are minors? So in order to define a minor, we need to define a model. Given two graphs, L, a small graph L, and a big graph G, we say that L is a minor of G if there exists a so-called L model. An L model maps every vertex of L into a connected set of vertices called a branch set in such a way that those branch sets are pairwise disjoint, and whenever we have an edge between some two vertices x and y in the graph L, then there should exist at least one edge between the corresponding branch sets, the branch sets corresponding to the vertices x and y. Yeah, so that's the basic definition that we will be working with. And now let me show you some history of graph minors. I will show you first two historical results and then two results by Robertson and Seymour and how they relate to those two historical results. So the history of graph minors starts with Wagner's theorem, who characterized planar graphs as those which exclude K55 and K33 as a minor. This is a fairly simple consequence of Kuratowski's theorem, which proves the same but for topological minors instead of minors. And basically the proof is to show that whenever we have K55 or K33 as a minor, then we can also find a subdivision of K55 or K33. And if you do some case analysis, you can show that it's always possible. Yes. And this is a very easy consequence of Kuratowski's theorem, but it's important to us because, as we will see, it's a special case of a much more general and very deep results in graph minors. Let us now observe also that planar graphs are not the only class of graphs which can be characterized by forbidden minors. Another example is forests. Forests are exactly K3 minor free graphs because there is equivalence between cycles and graphs and K3 minors. So that's the first historical result. The second historical result may be a bit controversial because usually it's not formulated in terms of graph minors, but it's Erdős-Fosa theorem, which can be seen as the first structure theorem for graph minors. We can observe that, as we mentioned earlier, there is a correspondence between cycles in the graph and K3 minors. So a graph contains P disjoint cycles if and only if it contains PK3 as a minor. And Erdős-Fosa relates graphs excluding this minor to so-called K-apex forest. So a K-apex forest is a graph from which you can remove K vertices so that whatever remains is acyclic, so it's a forest. And Erdős-Fosa Edwards with Posha showed that the classes with graphs without many disjoint cycles are actually equivalent to K-apex forests. They showed that. Oh, I can hear some echo. So Edwards with Posha showed that if you exclude the graph on the left as a minor, then you get this structure on the right. So you can remove a small set of vertices so that the graph becomes a forest. And conversely, if your graph is a less than K apex forest, then it excludes many disjoint cycles. And this is the shape of this theorem is something that's very common in graph minors, where we have some decomposition for graphs which exclude minors of specific type. In this case, it's T-disjoint triangles, but in general, we will consider more interesting cases where the most difficult general case is where we exclude a KT minor. And then the structure is the most complicated. Okay, so those were two historical results. Now let's go. I can hear people. I can hear voices. Are there some questions?
That was just by accident.
Okay, so let me continue. So now we enter the graph minors era. This is a seminal series of papers by Robertson and Seymour, and we will see how the results from these papers relate to Wagner's theorem and this Edwards-Posha theorem. First, we have this big generalization of Wagner's theorem, which basically says that if you take any class of graph chances which has any class of graphs which has a chance of being characterized by a finite list of forbidden minors, then it really is the case. Namely, every minor closed class of graphs is characterized by a finite list of forbidden minors. In the case of planar graphs, those are two graphs. In forest, it's just K3. And Wagner's and Robertson-Seymour theorem asserts that it's possible for every minor closed class of graphs. Another result, which is related to Edwards-Posha theorem, you can see that it has a really similar shape, is the characterization of KT minor free graphs. So the graph minor structure theorem from the title of my talk. KT minor free graphs can be, this theorem asserts that KT minor free graphs are basically the same as K decomposable graphs, where the K decomposable graphs will be defined in a moment. For now, you can see the illustration by Felix Reidel, which shows that any such graph can be decomposed into a tree of nicely structured nodes. Okay, so now since we started talking about graph minors, let's talk about some applications of this theory, something that might interest you even if you're not interested in graph minors. So first of all, we already discussed two of those. We told about structure theorem for KT minor free graphs, and also forbidden minor characterization. Another result of the graph minors series is an FPT algorithm for the K disjoint paths problem, where you are given a graph G and K pairs of vertices, and you ask if you can match those pairs of vertices with disjoint paths. More recent results that were not made by Robertson and Seymour are, for instance, low-two coloring of KT minor free graphs, or proof of clustered Hadwiger conjecture, or my recent project where we use graph minors theory to solve integer programs. It's quite surprising because it seems that it doesn't say anything about graph minors, but actually it turns out that when in our programs, bounded subdeterminants translate to forbidden minors, and the problem boils down to understanding the structure of some auxiliary graph. Now let's move on to the next part, where I will rigorously define this graph minor structure theorem, which describes the structure of graphs excluding minor. First, we need to introduce the notion of tree decomposition. most of you are probably familiar with the definition of a tree decomposition, but let's go quickly over it. A tree decomposition consists of a tree and the function beta, which maps the vertices of the tree into subset of vertices in such a way that every vertex of the graph G appears in a bags which induce a connected subtree of the tree, and every edge is contained in some bag. For each bag, with each bag we can associate a graph which is called a torso, and it's obtained as a union of the subgraph induced by this bag and all cliques on every intersection with adjacent bag. And we'll be interested in tree decomposition where torsos have quite nice structure. Next, we will define some parameters. The adhesion of a tree decomposition is the maximum intersection of two consecutive bags. So in this case, it's 4 because the intersection of the red bag and the green bag has 4 vertices. And the width of a tree decomposition is 1 more than the size of the biggest bag. And we define the tree width of the graph to be the minimum width of a tree decomposition of that graph. And with this, we can state the first structural theorem by Robertson and Seymour, or maybe first in this talk, which is the grid minor theorem, which characterizes n by n grid minor tree graphs as exactly graphs with bounded tree width. As a corollary, we deduce that for a planar graph L, if we exclude L as a minor, then the such graphs have a tree width, have bounded tree width. And this is a really nice answer to the question about the structure of such graphs, having a bounded tree width with a really strong property. The situation becomes much more complicated when we consider L-3 graphs for a non-planar graph L. And in order to formulate the theorem for such graphs L, we need to introduce some topology. So we will be dealing with surfaces. Our surfaces will have boundary. So for us, a surface is obtained from a closed disk by attaching strips to boundary and cupping caps. So for instance, we can start with a closed disk. This is a surface with 1 cup. And we can choose 2 disjoint intervals on the boundary and connect them by a strip. And if we attach a strip to 1 cup, then it's possible that the number of cups drops. Now we have 2 cups. And we can repeat this a number of times. Again, the number of cups drops. But if we add a cup between 2 distinct cups, then the number of cups may decrease. For instance, if we do something like that. Then there's this last operation which is mentioned above, namely cupping cups. If we pick our favorite cup, we can cup it by just gluing a closed disk along its boundary to that cup. And in this case, we would obtain this torus with 1 cup. Oh. So this is an example of a surface. Next, we define the notion of vortices, which is a special case of tree decomposition, where the tree is a path. So such a tree decomposition is a path decomposition. And a rooted path decomposition is a path decomposition where the underlying path consists of 1 vertex from each bag in that order. And we use vortices to decorate graphs embedded on surfaces. Given a graph embedded on some surface, we can attach a vortex along its boundary so that the paths on in the blue vertices of the rooted path decomposition are identified with the vertices on the boundary of the surface. And now we are ready to define the most important notion, namely the near embeddability. So this combines embedding on a surface, attaching vertices of bounded width on the boundary, and then adding a small set of vertices Z, which can be adjacent to anything in the graph. So another way of looking at this is that after you remove the set Z from the graph H, your graph decomposes into a union H0 of the graph embedded on the surface, and those vertices J1 up to Jm. And for k near embedding, we assume that the number of apices in the set Z is less than k, the number of vortices is less than k, and also each vortex has width less than k. And now we can go back to our drawing that we've seen earlier and explain what's going on. So a graph is LK decomposable if it has a tree decomposition where each torso is LK near embeddable, in the sense that it can be near embeddable in a surface in which L is not embeddable. For some technical reasons, we assume this to be slightly bigger than K, the parameter which specifies the complexity of the near embedding. But we also assume that the adhesion of this decomposition is bounded by K. And for convenience, we define K decomposability as a KKK decomposability. And with that, we can now formalize this graph-minor structure theorem from my title. So Robertson and Seymour showed that if you have an non-planar graph L, then L minor free graphs are LK decomposable for some K depending only on L. So as a consequence, this implies that KT minor free graphs are the same as K decomposable graphs. And this is the big result which we improved. We showed that dependency on K is at most polynomial in the number of vertices of L. Yeah, but it wasn't sure that such an improvement exists. In a survey written shortly after the proof of the graph-minor structure theorem, Laszlo Lowas wrote that it would be important to have simpler proofs with more explicit bounds. Warning, many of us have tried and only a few successes can be reported. And indeed, when he was writing that, we didn't know that much about the structure theorem, and there were not many improvements. The only useful thing that was simplified was the proof of the grid-minor theorem by Robertson and Seymour and Thomas. But now we know much more. We know that grid-minor theorem holds with polynomial bound. We know that the Flatwell theorem, which is one of the main parts of the proof, also holds with polynomial bounds, and we have two independent short proofs of that. And finally, the local structure theorem is also, we have a simpler proof, but which is still fairly complicated, and it gives us an exponential bound, and this implies an exponential bound for the graph-minor structure theorem. So now is our first result, the polynomial bounds for the graph-minor structure theorem. As I said, this is exactly the same, except that now the parameter K is polynomial in the number of vertices of L. Okay, so that's the first result, which is the most, so usually when people talk about graph-minor structure theorem, they mean that result. But in practice, it's actually a different theorem that's more important to us, and that's the local structure theorem. This is the tool for proving the graph-minor structure theorem, and also the forbidden minor characterization, and many other results. So in practice, it's the local structure theorem is a much more powerful tool. And we also improve that result. But first, we need to formalize, to state this theorem. Roughly speaking, the main difference between the local theorem and the global theorem is that this local structure theorem works for locally L minor free graphs. So we don't require the graph to completely exclude L minor, but just locally in some sense. And with this assumption, this local structure theorem asserts that we can decompose a graph into one central part, which captures this the large portion of this locally minor free graphs, here represented by a yellow shape. And there is any number of side parts, where each of them contains only a small part of the locally L minor free graph. So that's the main difference. There's also another difference, which is a bit technical and not as important. which asserts that there's a slightly stronger near embedding. We know a bit more about this embedding. We know that every triangle on the part embedded on the surface is spatial. And as I mentioned earlier, local structure theorem together with grid-minor theorem implies the graph-minor structure theorem. So actually, this is the main result for our talk, not the previous one. And from now on, I will just focus on this theorem and try to formulate it and talk a bit about the proof, how we prove it. So let us first start with this technical difference, which is not that important, but it will give you a bigger picture on what the local structure theorem is. So we say that, let us say that K near embedding is strong if every triangle in H0 is spatial in the embedding. So we exclude a situation where some triangle goes via a handle, for instance, or surrounds a vortex. This is not allowed. And now, if we know that we have a torso H of our graph, which is strongly K near embeddable in sigma, then we can translate it to a drawing of the graph G minus D. So assuming you have a strong K near embedding of this form, you can look at it differently, and instead of talking about torsos, you can talk about drawing a graph G minus Z on a surface with crossings, but with this assumption that the crossings happen only locally in some small disks which all interact with the outside world by at most 3 vertices. And also an important difference is that in this setting, you will not have bounded width of those vertices, but only a bounded adhesion. But this is that's the price that you need to pay. So basically, those are two ways to talk about isomorphic situations. We'll focus on this description in terms of a K near embedding because I think it's simpler. So this is this technical difference between the two approaches. Now the important difference is about this locally excluding a minor. And let me formulate it. So for an n by n grid model, so suppose that we have a graph G and some huge n by n grid model eta. We say that an L model mu, so a model of our non-planar graph, is rooted in this grid model if every branch set of the model of L contains at least one branch set of the grid. So that's one definition that we need. Roughly speaking, we will say that the graph is locally minor free if it doesn't contain an eta-rooted model for our favorite grid model eta. And we have this another definition of an eta central torso, which means that if we look at this torso and the adjacent bags in some tree decomposition, then the adhesion will be less than n. And moreover, each of those parts intersect less than half of all branch sets of the grid model eta. Actually, this condition implies that we can say much more about what's inside one such bag, and it's really a small part of the grid because this is n by n grid and the adhesion is less than n. So you cannot have like split grid in half and have half of the grid in one GI. So typically you can imagine that there's only a small part in each GI. So here's the main result, actually. So the polynomial bound for the local structure theorem. So together with Gorski and Widrech, we show that for every non-planar graph L, there exists some integer k, polynomial in the number of vertices of L, such that whenever you have a graph G and an n by n grid model eta, which is reasonably large, then either you can find an eta-rooted model of your non-planar graph L, or you can find this near embeddable torso of the graph G, which is eta central and LK near embeddable. So yeah, we can pause here for a moment. If there are some questions, then this is a good moment to ask them before we will talk. We will move on to the proof part of this talk.
Can you please repeat what it means to be eta central?
So eta central, this is so it's on the slide now. It means that the adhesion is less than n, and each of those side parts. So whenever you look at, so the idea is that you can. Okay, so formally you can think of this as having a star decomposition, a tree decomposition where the underlying tree is a star, and we require that in this decomposition, the central node torso has a really nice structure and captures the large part of the grid, and the other side parts can have arbitrarily complicated structure, but we know that each of them contains only a small part of the grid.
But this small is not that small, yes? It's n squared over 2, so it's almost half of all the vertices.
Yes, but in some sense, it's impossible to ensure that. I mean, this is enough. This is enough for our purposes to work. So in practice, what it means is that whenever you choose your side bags, those messy ones, you can always find the row and the column of your grid, so that the image under the model of this row and column is disjoint from this part GI. And this is not obvious why this condition is important, but I decided to skip doing a whole lecture on tangle theory and explain why this makes sense for the sake of putting more interesting stuff in this talk. I really regret that I don't have like 5 hours to spend here and talk, because I would really love to.
But so yeah, I have a similar question. So are you using somehow the bound on the adhesion? Because if you just cut off half the grid, then it could be possible that you don't have a row and a column of the grid contained in H.
Yes, I don't. It's not even possible that. I mean, I cannot achieve that. I have this because we can imagine a situation where you have a grid, and for instance, we can imagine that each GI contains completely one. Like we can imagine a situation where in each row and each column we have some branch set which is separated by a small set, and then those parts, each part will contain some branch set. So there will be not a single branch set which is completely contained in H. So yeah, so we cannot achieve this really strong situation where we have a really big part of the grid is contained in H. In particular, it's possible that the graph induced by the vertices of H is completely edgeless, and all the edges.
I understand. My concern is more, what if I just have H and a single GI, and half the grid lives in GI and half the grid lives in H? Then in the usual sense, the tangle of the grid is not centered on H.
I mean, it is, because the adhesion is strictly less than the side of the grid. So there's a unique big side and a small side. And if the small side cannot intersect half of the branch sets.
Okay.
Agree?
So you're using, so you're using the fact that your adhesion is small, and then this n squared over 2 bound really just becomes like linear in n.
I mean, it's still possible that I chop off like quadratic number of vertices. If I like take n-1 vertices really close to a diagonal, but it will be strictly less than n squared over 2. And it was the easiest way for me to define it. I see that it introduced some confusion, so maybe it's not the best way to define it.
Okay, okay. All right. I want to block it.
The only reason for this is that you have adhesion less than n. So all you want to have is that the major part of like the big side of when you cut the grid around these adhesions, that the big side is in H, not in GI. This is all you want.
Yes, I will repeat this because I'm not sure if this was heard from other people, but the question was whether it's the only thing that I care about is that if I take a separation defined by one bag and the rest of the one side part and the rest of the graph, then the small part doesn't contain the large part of the grid. So now that we discussed those details, let's move on to the proof part of the talk, something that is, I think, most interesting. The main result once again. And now we will discuss the proof. For those of you who are not experienced with graph minors, may be a bit surprised how from this purely combinatorial setting where we exclude some graph as a minor, we have this super strong property of being nicely embedded on the surface. And the answer is actually one theorem which is used over and over in the proof. And this is the two-path theorem. Let us consider the following setting. We have a graph G and two prescribed pairs of vertices, x1, x2, and y1, x1, y1, and x2, y2. And we want to discuss, we wonder if there exist two disjoint paths connecting those pairs of vertices. And there's one obvious situation where such paths do not exist. Namely, if our graph can be drawn on a closed disk so that the vertices x1, x2, y1, y2 lie on the boundary in that order. In such case, whenever we try to connect those pairs of vertices, they must intersect. And more generally, we can observe that if instead of having embedding of the whole graph, we can find a torso of that graph, which contains those four vertices and is embedded in the disk in that way, then we also can find the joint paths P1 and P2. Two-path theorem, which was rediscovered by many different people, but here I attribute it to Robertson and Seymour, asserts that this is the only obstruction to finding the paths P1 and P2. So they show that if such paths do not exist, then we can find the torso of H, which is embedded in a closed disk with the vertices x1, x2, y1, y2 embedded, contained in the torso and embedded on the boundary in the listed order. And moreover, we have this strong near embedding condition of every triangle being facial. In particular, this last condition implies that there are no k-force. So the adhesion of a torso is at most 3. So one of the possible outcomes of the local structure theorem is that we get a near embedding. The other outcome is that we get an L minor, which is rooted. So let us now discuss the next thing. How do we build an L minor? Usually, in most of the cases of the proof, we will not actually get an L minor, but a KT minor. So we will get a complete graph as a minor. So we will discuss this. So the problem with building a KT minor is that it's hard to build it incrementally. It's hard to add branch sets one by one, so that whenever we add a new branch set, it's connected to all the previous one. So instead, we will build our KT minor indirectly. First, we can see that KT is a minor of KTT, so it suffices to build a KTT minor. Next, the graph KTT is contained in the strong product of two paths, so a grid n by n grid with crosses in each square. We can put the line paths in two diagonal directions, and then every green path will be attached to the red path, so we have our KTT as a minor, and thus a KT minor. Finally, if you want to build this strong product of two paths, it suffices to find a long grid where the crosses are only in the middle row, because then we can just do this snake that collects crosses for many different rows. So now the problem boils down to finding a long grid where there are many crosses in the middle row. There is also another way in which we can build a KT model, which I will not give you any intuition why this holds, but it's not very surprising. If we have a very long grid, and between the vertices in the middle row, we have jumps, and many of them, so that no two of them are adjacent even. Then it suffices that you have roughly t cubed of them to build a KT minor. I don't think it's an optimal bound, but for now we're mainly aiming for a polynomial bound. Okay, so this is how we build a KT model. Now let us observe what's the main structure that we will maintain in our proof. This is some sort of partial decomposition where we decompose a part into this decomposed part G0 and an undecomposed part G infinity. And there's this intersection which is like the gray zone. Within that intersection, we will have a prescribed set of red vertices, which is not prescribed, sorry. We will have a set of apices, which will be contained in the intersection. And with respect to that set of apices, we will have a near embedding of the graph G0, which will be embedded on a surface with boundary in such a way that every blue vertex, so a non-red vertex from the intersection, is drawn on the boundary of the surface. And all the red vertices are apices. And the remaining part of the torso is embedded nicely on our surface. So that's the basic form of our decomposition that we will maintain. But there will be more ingredients that we need to make the proof work. First of all, we'll need to maintain a large flat grid submodel. So recall that in the statement of the local structure theorem, we are given a huge grid, huge n by n grid on the input. And in some sense, we want our partial decomposition to capture a large portion of it, like n over polynomial of t by n over polynomial of t. And what do we mean by contain it? Is that we mean that every branch set intersects the torso. And if we look at this mapping, which maps each branch set to its intersection with the torso, then this should define a model in our torso H. So it will be grid in the graph H minus Z even. And we also, for convenience, will require that it's embedded in a nice way so that the outer face agrees with the natural notion of outer face for a grid. So that's the one which contains 4 n minus 4 vertices. So yeah, that's the flat. That's one additional part for our decomposition. Another one is a nest edge. So around each cup of our surface, we would like to have a nest consisting of many disjoint cycles. Formally, by a nest, we mean a cylinder where one cup coincides with a cup of the surface from the decomposition. The other one is a cycle in our graph H0. And we also have some many nested cycles which separate the cups of the cylinder in the interior of that cylinder. And the number of cycles in this cylinder is the depth of the nest.
Then we have some additional vertices there, right? Except the cycles.
Yes, the nest, in general, the nest can contain very large planar parts, but the only thing that we need to make things work is that we have sufficiently many disjoint cycles which are nested and separate the two cups of the cylinder. Also, let me here point out that the white part of the decomposition will remain white no matter what happens. But the yellow part, the nest, this is something that's I think called battlefield in the graph minor series, and there this is the gray zone, which we don't know if it will end up in the white part of in forever. Maybe sorry, it will remain in the yellow part even. Maybe it will go white, maybe yellow, maybe we'll move those to apices, or maybe some other thing will happen, like it would not belong to the torso at all. Yeah, so here's our infrastructure. We have a partial surface decomposition, a flat grid model, and deep nests around the cups. So I will not specify yet what is the depth of the nest, but it will be sufficiently large and polynomial in the number of vertices.
An AP system go to mass the grid everywhere, right? There is no restriction.
Apices, the red vertices, are not embedded, but they can be adjacent to everything. That's correct. Yes, and moreover, we will need to maintain some additional invariants, which will imply that for in our partial decomposition, the total number of the apices and the Euler genus of the surface will not explode. We allow the number of cups to explode. It is unbounded. There may be arbitrarily many of them. We will reduce the number of those at the last stage of the proof. Okay, so so I have this animation here, which shows how we will extend this decomposition. We know how to extend the surface. You just attach a strip between two cups. And similarly here, we will find two segments belonging to one or two cups, and then extend the decomposition by finding a strip and adding only a polynomial number of vertices to the apex set. The most tricky part of the proof is how can we ensure that when we do that, the total number of vertices will not, in the apex set, will not explode. And yeah, as I mentioned, this is implied by the additional invariants, which I will explain later. For now, please believe me that we can extend those strips in such a way that this will be bounded. And also the Euler genus will be bounded. So essentially, there are three steps that we need to do. First, we need to show that there exists some partial decomposition which satisfies our invariants. And this is this uses a result which is known as flat-wall theorem. But yeah, basically it boils down to showing that that we can find a partial decomposition on a disk which contains an n by poly of t by n over poly of t subgrid, which is flat in the decomposition. Then we'll describe this strip extension procedure, which allows us to extend the decomposition in a way which preserves the invariant.
So n was the side of the original grid.
Yes. Yes. We start with an n by n grid in the local structure theorem. So first we find some decomposition, then we describe a procedure for extending it, and we greedily, exhaustively extend it until we reach a point where we can no longer apply this procedure to extend it. In this case, we go to the last stage where we do this thing where we reduce the number of cups and show that we can build a near embeddable torso which satisfies the local structure theorem. So the first part is the flat-wall theorem, and we are happy to announce that we have a new proof of this. And it's not necessary to have a new proof because in some sense, the existing proofs give better bounds. Like the proof by Chuzoi gives basically tight bounds asymptotically for this theorem. But we are really proud to say that we have this proof, which is, we believe, the simplest proof of the flat-wall theorem, which gives polynomial bound, and the exponents are not so terrible, like t to 3 and t to 4. And the proof uses a so-called frame technique. It's unfortunately, I don't have a lot of time to discuss this here, but yeah, this is the first part. And how do we use this theorem to build our initial partial decomposition? Well, we need to first we start with our n by n grid eta. Then we apply the Blackwell theorem to find a small set of apices, such that after removing them, we can embed the reasonable size subgrid into a disk in a flat way. And finally, we sacrifice some part of the outermost cycles in the grid to create our nests. Recall that we require our partial decomposition to have this property that every cup is surrounded by a nest. In case of a disk, we only have one cup, which is the outer face.
So what do you mean by grid submodel? Grid submodel of beta prime of beta.
Grid submodel. I think the drawing here is self-explanatory.
So just the branches?
Yes, I
one to one?
One to one. Every branch set of the one. Yes. So that was the first part. Let's assume that we already have our starting point, some partial surface decomposition with nice properties. The next step is, as I discussed, a strip extension. We will be working in a graph which consists of the nest part of the torso, so h of n, union the undecomposed part minus the apices. So this is represented on this figure here by those nests, and then we have this brown part, brown undecomposed part, which attaches to the cups of the surface, so the blue cycles. And we will show that if we can find two disjoint segments on the outermost cycles of nests, of two distinct nests or one nest, if you have many disjoint paths in this graph that I described, then actually you can find a slightly smaller subset of paths which spans a nice strip with which we can extend our partial decomposition. And again, we will do this in steps. First, we will start with some very messy linkage, which consists of disjoint paths, which can go back and forth into a nest and visit other nests.
So G infinity is the undecomposed part, right?
Yes, G infinity is the undecomposed part.
What is H of n?
This is the subgraph of the torso that's induced by the nests. So we have like a mixed graph. Part of it is a torso, and part of it is not a torso, but a graph G itself. So in some sense, the cups corresponds to also to those part of the graph G that are attached to this.
They are just, you don't know anything about them. They are just...
Yeah, I don't know about anything about them. I only consider the embedded part, like the flattened part of this graph. In a way, it's embedded in the surface.
And go to this, yes, to this unknown stuff. Yeah, this is what you mean. When they're going up there, this is this ground thing at the top.
Yes, I consider this graph, which is the union of the net part and the undecomposed part. So in this graph, I ask whether you can find many disjoint paths between two purple segments, where each purple segment is contained in the outermost cycle of some nest.
And the Z, what is the Z?
Apices.
Just the total.
Yes, once something goes to apices, I can just remove it. But thank you for asking. If there are any other questions, please interrupt me and I'll be happy to answer.
Yeah, no, sorry. So when you say transaction, are you using like the transaction in a society, or are you using a linkage between two of the distinct cups?
In here, like here, by a transaction, I mean a linkage between two purple graphs in this particular graph. Yeah, I guess this is not exactly a transaction in the traditional sense.
Okay, so yeah, so you're just looking for a linkage now between two cup sets.
I'm trying to, so the main difference between our approach and the original approach is that we have multiple cups. In the original proof, it's the proof tries to somehow, whenever there appears an extra cap, it tries to separate the two parts so that we can handle each of them independently. And in this case, we have multiple caps, and we are asking if we can find a large linkage between two segments. And those two segments can be either contained in two distinct nests or in one and the same nest. I just realized that I forgot to mention something that's written on the top of this slide, namely that I consider the nests to be tight. In a sense, I want them to be inclusion minimal. This way, I will know that I will not have like a huge transaction which goes completely inside the nest. And I will indeed be able to create a strip extension.
But so you're just using now a linkage? So you're just using Wagner's theorem to find these green paths, or do you need to find a crooked linkage so that it goes through the vortex?
I find any linkage, and from any linkage, I have no assumption at all about the linkage. I will in the proof I just massage the linkage and make it nicer and nicer to the point where I just obtain a flat strip.
So the linkage is much bigger than the depth of your nest, and then you're using tight to make sure that it doesn't stay inside the nest?
That's correct. The size of the linkage is huge. This is one of the biggest parameters in the proof. The only bigger thing is the size of the grid.
Okay, thanks.
Okay, so back to the strip extension. Suppose that we can find the situation like on the left. We have two segments on the outermost cycles of nests and many paths between them. And now we'll try to build a strip extension from that. So after removing only a polynomial number of vertices in T, we would like to a part of the graph to be flat and contain many of those paths. We will achieve this in 4 steps. The first step is, so we start with an arbitrary linkage, which can be completely messy. In the first step, we show that we can actually make it nice, so that each path in our linkage consists of 3 segments, where the first segment is contained in the first nest, the last segment is contained in the other nest, and the remaining part is disjoint from the 2 nests involved, or the 1 nest involved. But it may still intersect other nests. For that, we don't know yet. We'll go back to that after the step 3. In the second step, so yeah, I will not say all the details about how we do everything in each step. But yeah, the first step is that we orthogonalize the linkage. In the second step, we apply Michał-Seweryn's theorem to ensure that our linkage is monotone, in the sense that the endpoints in one nest are in the same order as in the other nest, or maybe reversed. But for simplicity here, I just assume that they go in parallel. Then in the third step, we apply a flat wall argument. So roughly speaking, what we are doing is that we're repeating the proof of the flat wall theorem on this special grid, which is formed by the paths in our linkage and the 2 nests. Like we know that each nest contains many disjoint cycles, so we can imagine a large grid which contains one half in the one nest, the other half in the other nest, and then we have many paths corresponding to the middle row. And we show that we can basically a similar thing as in the proof of the flat wall theorem to ensure that after removing a polynomial number of apices, we can find a nice embedded strip which contains many of the paths in the linkage. That's how we go from that's the step 2. The step 3 is actually, no, sorry, this was the step 3. For the step 4, we need to ensure that we can make our strip disjoint from the nests. And this may seem like a tricky part because, okay, the nests are tight. And this fact implies that they cannot span across many paths in our strip. So they are more or less contained locally. So maybe we can find some section of the strip which is disjoint from them. Yeah, but this won't work because the number of caps is unbounded. So we need to be a bit smarter. So what we actually need to do is that we need to observe that if there are caps that are in many different places, then you can find many jumps between pairs of them. And then if you have this, then you can build your KT minor. So one possible outcome that you get in the step 4 is that you find many jumps between independent nests. And this will imply a KT minor. So
Sorry, you muted yourself.
Sorry? I muted myself?
I can still hear him fine. Everything's normal.
Okay. If there is still some problem, let me know. Okay, so in this journey from a large linkage to a flat strip, there are two moments where you can get a KT minor. One is in the step 3, where we apply the flat wall theorem, and the second is in the step 4, where we get many jumps between nests. But in both cases, we need to somehow argue that this is rooted in our initial grid model, or at least in the flat model contained in the partial decomposition. For that, we need to have some assumption about linkedness between the grid model and the nests. And this is a bit technical property. I will not define it very rigorously, but roughly speaking, we want to have this property that whenever we choose a polynomial number of caps, say t cubed, and for each of them we want to send some linkage of size, say, t to the power of 10, then as long as the values are not too large and the support, so the number of non-zero values is not too large, we should be able to find a large linkage which connects the top row of the flat nest to the slightly shrinked nest, where how much we shrink the nest depends on the size of the support. Like, this is some technical assumption that needs to be done to make the proof work. And I'm not going to discuss this in a bigger detail, but this, I hope that this explains that if we find our KT model from applying the flat wall theorem to a strip, we can somehow use this linkage to make the model rooted at the grid eta prime, and thus in eta. Similarly, if we get many jumps, then we can send disjoint linkages to those nests, which are connected by jumps, and then connect them to obtain this long grid with many jumps in the middle row. In both cases, we get a KT minor, and we are happy. Okay, so for now, we were working under a very optimistic assumption that if we do this procedure, neither the genus of the surface explodes nor the number of apices explodes. So let me now tell you what are the invariants that we maintain to have these properties. First, in order to ensure that we have a bounded surface, we will maintain as a minor a universal graph for surfaces. So we will contain as a minor some graph which contains as a minor every graph embeddable on that surface, assuming that it has at most t vertices. More precisely, we'll use a recent construction of universal graphs by Gavoy and Hilaire. And let me describe the construction that they use. So they construct graphs embedded on surfaces. So they build a graph together with an embedding. They start with an n by n grid, where n is sufficiently large, and it's embedded on a square so that the outer cycles of the grid coincide with the boundary of the disk. And then they add those strips between some disjoint paths on the top row. And together with each strip, they also embed sufficiently large matching in that strip. And so
they are different. One is like crossing and the other is not.
yes, there are different ways you can embed those paths. And yeah, if you want to have a non-orientable surface, then you need to have a strip like the red one. But for now, I was like avoiding talking about orientability because I don't think that's really the clue of the proof and the most interesting part. So yeah, Gavoy and Ilek said that if you choose the width sufficiently large, if you choose the width of the strips to be sufficiently large compared to the number of strips, then every graph embedded, which is embeddable on the surface sigma u obtained by square and strips, if it has less than 3 vertices, then you can find it as a minor. This is a nice generalization of the fact that if you have a sufficiently large planar grid, then you can find a any planar graph as a minor in a grid. So what we do in our proof is that we maintain such a minor, and this way we know that we will never have two. So the surface sigma u will not be necessarily the same as the surface in our decomposition, but it will only differ by the number of caps. So exactly the same graphs will be embeddable, and if we manage to maintain such a minor, then we will know that we will never have a too complicated surface, because then we get an L minor. This is an only situation of the proof where we get an L minor, not a KT minor, and it will be rooted in our surface, in our grid model. Sorry. So that's how we deal with bounding the surface. For bounding the apices, we need something different. Namely, when you go back to strip extension, oh yeah, I didn't mention, but basically the idea is that we can maintain the invariant about the surface, because whenever we have our strip extension, we can use this new strip to extend our existing grid model. Sorry, existing universal graph model. So for the apices, we will also do this. So in order to ensure that the number of apices is bounded, is that we will have some incremental model of KT that we build. And we will ensure that whenever we add a new apices to the apex set, then we will get a new cross in some long sequence of crosses. So if this happens too many times, then we get a KT model and we again win. So in order to achieve this, so we achieve this by taking this argument that we had for strip extension that we had originally. And then once we have our potential strip extension with a polynomial number of apices, we try to push them back to the strip. So we basically apply a two-path theorem to the strip union apices. And either we succeed, in which case it turns out that the apices were not actually necessary, and we have a strip extension with no new apices, or we find a cross, which contributes to our KT model. Yes, so that's roughly speaking how we do the strip extension. Now we do this procedure for as long as possible. We know that the number of apices is bounded. We know that the number of the surface is bounded. L is not embeddable in it. So the only part that remains is to say is what happens if we no longer can apply this extension procedure. This means that whenever you pick two purple segments in our graph, you will have only a bounded number of paths between them. In such case, we will do some cleanup where we will reduce the number of caps. So first, we will use some Erdős-Pósa style argument to show that you can remove a polynomial number of vertices from the undecomposed part, so that almost every cap is isolated, meaning that it's basically attached to some components of the undecomposed part which are not attached anywhere else. In the second step, we will apply a two paths theorem to each of those isolated parts. And again, if it happens that we have too many crosses, then we combine them into a K-team model. So we assume that only a small number of those is not flattened and cannot be capped. So at this moment, we end up with only a polynomial number of caps, and then we can isolate them by applying pairwise Menger. And because this is the last step of the proof, we don't really care that this set will be very large. Like as we said, the linkages that we find between purple segments are very complicated. But this is the last step of the proof. So even if we remove a huge number of apices, then it's not a problem for us. Yeah. So basically, after you do that, you can we end up with a situation where every cap is isolated, and there is only a polynomial number of those. At this step, we can turn those caps into vertices. It's possible that when we are applying Menger, we killed the whole yellow nest around some cap, but it doesn't bother us. The only thing that we need to know is that there are no large transactions. Now I'm really talking about the transaction in the original sense. I know that in each of those local parts and attached to distinct caps, I won't have a large transaction, and therefore I can find a path decomposition with bounded adhesion, which in turns can be turned into a bounded width vortex in a torso, which is near embeddable in the same surface as the one in our partial path decomposition. And basically, that's the proof. All the important ideas that we used. Here is the summary of the proof. First, we find an initial partial disk decomposition using a Plattwall theorem. Next, we describe the invariant that we need to maintain. Then we have exhaustively extend the procedure with the strip extension procedure. And finally, if we have no longer large transaction, then we do this cleanup stage where we can build our near embeddable torso of the graph, which is eta central and LK near embeddable. And that's it. Thank you very much.